Welcome! In this module, we will get a broad overview of detachment processes. Earlier in this course, we calculated the flux of substrate into the biofilm for steady-state conditions. Substrate diffusing into the biofilm leads to growth of bacteria in the biofilm. Question: how can there be a constant steady-state biofilm thickness if there is continuously new biomass being produced by growth? On one hand, there are decay processes that balance growth. But in addition to decay, there must also be detachment processes balancing growth. This module is focused on these detachment processes. At the end of this lecture, you should be able to explain different mechanisms for the removal of biofilm, i.e. detachment. Prepare a material balance considering growth, decay, and detachment. And to use the material balance to calculate steady-state biofilm thickness predictions. Here's a schematic of a biofilm. And let us now prepare a mass balance for the biomass in this biofilm. Accumulation is shown on the left. The terms on the right refer to biomass growth, decay processes to remove biomass, and then the detachment processes. Detachment is usually considered a process removing biomass from the biofilm surface. In the literature, we find a diversity of detachment rate expressions, as is shown in this table. Some detachment rate expressions are linked to the biofilm thickness. Other expressions are linked to shear or to growth rate. There is a diversity of detachment rate equations, and we do not really have a good understanding of what equations to use in what type of reactor, and also not a very good quantitative understanding of rate coefficients. But let us take a look at the benefits of explicitly modeling biofilm detachment. We will do an example assuming the highlighted detachment rate that is proportional to the biofilm thickness LF. Here we prepare a mass balance. Each term in this mass balance has dimensions of mass per time. The term on the left-hand side of this equation describes accumulation. The first two terms on the right-hand side represent biomass growth and decay per unit time, respectively. The last term on the right-hand side is the biomass detached from the overall biofilm per unit time. We now assume first-order kinetics and substitute the corresponding substrate flux. We assume steady state, and then we divide by the surface area AF and the biofilm biomass density XF. Next, we rearrange this equation to get an explicit equation for the biofilm thickness. We see that the biofilm thickness increases with increasing substrate utilization rate and increased bulk phase substrate concentrations. And the biofilm thickness decreases with increasing decay and detachment rates. This makes sense. This result is very plausible and allows to predict biofilm thickness. This is useful, but one major problem is that neither detachment mechanisms nor the kinetic parameters in the detachment rate expressions are well understood. One consequence is that many commercial simulators simply ask users to provide a fixed biofilm thickness as a model input rather than predicting biofilm thickness as a model output. If we look at the diversity of biofilm reactor types, then we can also expect a broad range of dominant detachment mechanisms. In some cases, continuous erosion and abrasion will dominate. In other cases, detachment is a dynamic process triggered by dedicated backwashing events or spontaneous sloughing or breakup. It is obvious that a simple detachment rate expression will not be able to predict this diversity of processes. Here's a cartoon version of different detachment processes. Note that simulators are usually assuming that detachment removes biomass only from the surface of the biofilm. They do not model sloughing. But in practice, sloughing can remove larger parts of the biofilm. The type of detachment will in turn have significant impacts on the competition of bacteria in the biofilm. Mass balances for biomass can get even more complicated. In addition to growth, we need to also consider attachment processes. If there is active biomass in the bulk phase, for example, in an IFAS reactor configuration, then we need to consider attachment of bacteria from the bulk to the surface of the biofilm. Next, we need to consider a certain movement of bacteria within the biofilm. And then we also need to consider attachment and detachment of particulate organic matter to the biofilm surface and transport and hydrolysis of particulate organic matter in the biofilm. In addition, we need to consider the influence of detached biomass on the bulk phase microbial community. Detachment of active biomass results in a constant seeding of the bulk phase. In IFAS system, this seeding can in some cases maintain nitrification by the activated sludge, even if solids retention times of the activated sludge would otherwise result in washout of nitrifiers. So the take-home messages from this module are the following. Biofilm modeling always considers biofilm detachment. This can be done explicitly, assuming a detachment rate expression. This is resulting in a constant biofilm thickness as a model output from the balance of growth, decay, attachment, and detachment. But modeling often considers detachment only implicitly by assuming a constant thickness biofilm. This is resulting in a biofilm detachment rate that balances growth, decay, and attachment for this given fixed thickness. Many commercial biofilm simulators assume a constant biofilm thickness. Detachment rate models are often a function of the biofilm thickness or the biofilm thickness squared, but factors influencing detachment are not well understood. And ultimately, detachment and attachment are three-dimensional processes that are really difficult to capture in one-dimensional models. Mechanisms of biofilm detachment are very different for different types of biofilm reactors. Competition in biofilms is influenced by this detachment.